Hello there. In this video, we're going to cover another aspect of the Ciw Python package. In the last video in this series, we looked at process-based routing, where we could predefine a sequence of nodes that a customer would go through once they've entered the network. In this video, we're going to do what Ciw calls flexible process-based routing, which allows for you to have some choices, some branching points in deciding which way a customer goes or doesn't go as they flow through the system. So let's go through a coded example here. Let's go import Ciw, and we'll define a routing function, just like the process-based routing. And we'll say individual needs to be of individual type, and we will say that there's going to be a simulation object passed in, and that needs to be of a simulation type. And we will decide that the type annotation here, as was the case before, is going to be a list of integers. Okay, so what should we put in this? We'll keep it simple, but it's a good starting point for what's different in this video compared to when we looked at the original process-based routing. Is here, you can see that yes, I'm passing in a list, but actually it's a list of lists, and that should give me a hint. I need to update my types to reflect that. It is a list of lists of integers, not a list of integers as before. So we've got 1, 2, and we'll just say that that returns. So it's a little bit different. What does this get us? Well, let's keep building out the structure of a network. So let's say we define our network object, and we're going to use the interface create network to do that. So arrival distributions, we'll start there. Nothing's going to be different in this particular piece of it. We're just going to say that for the first few nodes, there are no arrivals. And then we'll say that Ciw at the fourth node, we have arrivals that follow an exponential distribution with a rate of 1. All right. And then we'll look at the service distributions. Also a list, and in this case it's a bunch of exponentials. I might even just cheat here and grab one from the arrivals, and in this case they're all 2. We'll just copy 4 of those, so there's our 4 nodes. There is, with frameworks like this, a fair bit of ceremony to setting up a model, but it is kind of inevitable that for the more complicated the types of models that you want to describe, while still having a fairly general thing, you need to specify a lot. Okay, now we're getting to routing, which is really what this video is all about. Ciw.routing, and instead of a process-based, we'll put in flexible process-based. Now, if I'm being honest, I think that it's a little bit of like it makes it feel tacked on to the package that it's like called flexible, as if the original one wasn't flexible. I don't know the history of the development there, but it does feel like the type of thing that was kind of added afterwards, realizing that the original implementation was not as general as desired. Could be wrong though. So there's a few different pieces that we need here to make flexible process-based routing work. So the idea, to go back to this, is that it's still a sequence, as you can see, but it's a sequence of lists, and these sublists represent collections of nodes that are allowed to be in the first nodes visited. It could be 1 or 2, but it can't be 3 in that first batch. And then the second node in the trajectory has to be a 3. But then the third node in the trajectory could be, again, a 1 or a 2. So how do we decide where they actually go? That's what the rule is all about. That means, so what are some of the rules here? One is any. So if we said rule is equal to any, this means that just one node from each set should be visited in the order of the sets as we give them. They're not technically Python sets, but they're conceptually sets. The choice of which node is chosen from each set is the set with the choice keyword. So there's another keyword here, choice. And choice, there's a few different options. There's random. There is also JSQ for join shortest queue. And there is also LB for load balancing. And we've seen those as routing methods before. And if you go with any, then it's going to use whatever this rule is. Either random means, I believe, uniformly selected according to, like selected at random according to a uniform probability distribution, or according to this join shortest queue, or to this load balancing routing behavior. So rule any basically means follow the choice function. But there's an alternative here of any, which is all. And all means that every node in a set must be visited before moving on to the next set. The order at which the node is visited in a set is set with the choice choice keyword. So in other words, in this, instead of saying, well, it could be 1 or 2, it actually has to be 1 and 2 have to be visited before you move on to 3. But there could still be some logic around maybe it visits 1 and then 2, or 2 and then 1, that this all rule says you got to visit all of them, whereas the any means you got to visit one of them before moving on to the next set. So I believe that's just about all the ingredients we need for defining this simulation. Maybe let's put this back to any just for the moment. And let's set up a simulation. So we'll just copy from the documentation here. I'm not sure I feel like typing out all of this, so let's just paste it in, clean it up a little bit. I was just thinking about another video where I said we should get rid of the word cleaning from all software, and it's true. It's just such a vague term. Like, what do I really mean by cleaning here? Oh, and I also called this network rather than N. Okay, we should be able to run this now, so let's give it a go. If I go flexible, that's probably enough. So we get these trajectories of first of all, they have to arrive at 4, because that's the only place that they actually arrive at all. And that's maybe a non-obvious point about this example. We spent all that time thinking about 1, 2, and 3, but actually there's also a 4th node, and that's actually the only node that they arrive from. And hence this first column is all 4s, showing that this is showing the trajectory that they take. And then, you know, we see either a 2 or a 1 in that first column, and that exactly matches this. It could be either of them, and then it's 3s here, which correspondingly here, you know, is 3, 3, 3, 3, 3. And in this last one, we got 2s and 1s, and similarly, you know, this routing behavior says that you should visit a 2 or a 1 for the 3rd node that's visited, and then leave the network. So that's the gist of the any rule of visiting at least 1, and the flexible based routing is just to say, again, that we can do some branching behavior of saying, well, instead of it having to be exactly like 1 and then 3 and then 1, you maybe could do for some of them that it's 1 and then 3 and then 2, or 2 and 3 and then 1, and other kinds of different paths are implied by this possibility. And here we've done random, but of course we could have picked, you know, load balancing, for example. Should also work fine. Do we get any kind of different answer? I don't think. Oh, we get a little bit of a different answer in the final arrival. And this is going to depend on seed number details that don't really matter anyway, for how that actually turns out. So we can run maybe one more example here of, like, let's go all, just to see how that's different. And you can see that the trajectories are longer, because it's saying that in each of these sequence of lists, you have to visit all of them. You have to visit 1 and 2. But it doesn't specify, if I'm correct here, the order, right? Like, so they're all 4s in the first column. But in the second column, for the second node visited, you got 2s or 1s. And then similarly, whichever one wasn't visited first is visited second. We still have our 3s. And then again, we've got a kind of mix of 2s and 1s for the final 2 nodes. So that's one thing to keep in mind when you're using either any versus all, is that all really means you got to visit all of them, which means longer sequences. That for all, this is going to be a sequence of node visits that's actually, in this case, 5 long, whereas the any is going to be 3 long. But that provides you a bit more branching behavior for these trajectories. I still don't think that this is like maximally flexible in the way that I would want. Maybe maximally flexible is, first of all, vague. But what I mean is, like, it'd be nice if there was simultaneous crossover of it, like, depends on the individual, not just when they arrive, which is, I believe, when this routing function is called to decide their kind of destiny, but also it's like maybe the customers themselves should have internal properties. And maybe I'll show this in a future video, maybe not, but like you can actually get that by as you make your patient flow through these various kinds of functions in the Ciw Python package, that you can dynamically assign new attributes, including keeping track of like their history of where they've been, or you can grab it from their records and stuff like that, just to do some fancier stuff with the routing of going like it's path dependent, but the path is kind of randomly evolving in a way that I'm not sure you could even quite do with this flexible process-based thing. So that's something to keep in mind, is if you find this too limited, you're not necessarily dead in the water, but it is a good starting point to think about the process-based. Maybe you can randomly sample over a bunch of trajectories if that distribution can kind of be defined ahead of time, and if not, maybe flexible process routing, and then if not even that, that there's some other kinds of workaround things you can do with Ciw. All right, that is enough for this video. I will catch you in the next one. Take care.